TF.Keras model.predict is slower than straight Numpy? Thanks, everyone, for trying to help me understand the issue below. I have updated the question and produced the CPU-only run and GPU-only of the run. In general, it also appears that in either case a direct Numpy calculation hundreds of times faster than the model.predict. Hopefully, this clarifies that this does not appear to be a CPU versus GPU issue. If it is, I would love an explanation. Let's create a trained model with Keras. Now let's recreate the model.predict function using Numpy. We can easily verify these are the same function, module machine errors in implementation. We can also test out how fast these functions run, using IPython. I get that predict runs about 10,000 times faster than model.predict at low batches and reduces to around 100 times faster at larger batches. Regardless, why is predict so much faster? In fact, predict isn't even optimized. We could use number, or even straight rewrite predict in C code and compile it. Thinking in terms of deployment purposes, why would manually extracting the weights from the model and rewriting the function be thousands of times faster than what Keras does internally? This also means that writing a script to utilize a .h5 file or similar may be much slower than manually rewriting the prediction function. In general, is this true? IPython output, CPU. IPython output, GPU.
We observe that the main issue is the cause of the eager execution mode. We give shallow look at your code and corresponding results as per CPU and GPU bases. It is true that Numpy doesn't operate on GPU, so unlike TF.Keras, it doesn't encounter any data shifting overhead. But also it's quite noticeable how much fast computation is done by your defined predict method with NP compared to model.predict with TF.Keras, whereas the input test set is 10 samples only. However, we're not giving any deep analysis, like one piece of art here you may love to read. My setup is as follows. I'm using the Colab environment and checking with both CPU and GPU mode. TF1.15.2, CPU. Now, running your code. We can see that the execution times are comparable with old Keras. Now, let's test with GPU also. TF1.15.2, GPU. Now, the execution time is also comparable here with old Keras and no eager mode. Let's now see the new TF.Keras with eager mode first and then we observe without eager mode. TF2.4.1, CPU. Eagerly. Now, running the code with eager mode. Disable eagerly. Now, if we disable the eager mode and run the same code as follows, then we will get Now, we can see the execution times are comparable for disabling the eager mode in new TF.Keras. Now, let's test with GPU mode also. TF2.4.1, GPU. Eagerly. Disable eagerly. And lastly again, if we disable the eager mode and run the same code as follows, we will get And like before, the execution times are comparable with the non-eager mode in new, TF.Keras. That's why, the eager mode is the root cause of the slower performance of TF.Keras than straight Numpy.
Another answer is more useful in terms of how to make TF.Keras predict faster, but I think the following can help more in terms of what is it doing that takes so much time? Even with eager mode disabled, you might be curious to see how execution looks like, for example with or without providing batch_size, etc. To answer this question you may find tracing profiler to be useful. Tracing execution is adding a lot of overhead, especially for the places that have a bunch of very lightweight Python calls, but overall should give you quite a bit of insight into what part of Python code is being executed, because, well, it just logs exactly what is happening. You can try PyTracing since it produces files that Chrome browser visualizes nicely on its built-in Chrome column//tracing page. To use it for example in Google Colab you can do the following. First, install PyTracing. Then generate trace. Then download trace. After this in Chrome browser open, Chrome column//tracing page, click load button, and select trace.out file you've downloaded. You'll see something like the following. You can click on any element, see the full name of the Python function and file it is from plus wall time it took. Again, all of this is higher than in normal runs due to tracing overhead. You can see how disabling/enabling eager execution or changing the batch size will change the output and can see for yourself what is taking the most time. From what I currently see, in non-eagerly mode plus call like, model.predict x column 1000, batch_size equals 1000, quite a bit of time is spent on standardizing your data, whatever it means, ~2.5 milliseconds, including tracing overhead. Preparing callbacks, even though we didn't set any, ~2 milliseconds, including tracing overhead. As to the statement that Numpy version is not optimized, I wouldn't agree. The Numpy implementation here is quite optimized. Python is not making any pure Python calls in it. Execution of predict only results call to functions in C. I couldn't believe it at first but it seems to be the case, so overhead from Python is really minimal. You might gain a little bit by optimizing the way you do ReLU and eliminating extra allocation/deallocation, but that could only result in a very minor perf improvement.
As others have pointed out, the TensorFlow binary in question was compiled for GPU optimization. While GPUs are excellent at intensive number crunching because of the extremely high number of computing cores they have, they're painfully slow when it comes to moving data back and forth. When a model is executing on a graphics card, all the necessary data has to be burst over to the GPU. It has no access to the host system's RAM, nor does the host system have access to the video memory. Once the GPU is finished processing, any results have to be shipped back over to the host system. All of this moving around of data takes a great deal of time. Moreover, a TensorFlow binary compiled to execute with a GPU/CUDA does not, to my knowledge, include any of the standard optimizations for executing on a CPU, like using faster extended instruction sets, for example AVX, AVX2, etc. So you're comparing a highly CPU-optimized scientific library which can process data without even having to go back to RAM half the time, CPU registers and cache storage on the chip, to code that has to collect every last bit it's going to need before having to ship all of that data to the graphics card, and back. I'm also leaving out all of the data manipulations that goes on under the hood of TensorFlow. It works on its own data structures, after all. Eager execution is also another layer of inefficiency, I suppose. As for best practices in deploying Keras models, I'm of the opinion that it's like everything else in software, premature optimization is the root of all evil. If you don't need it to be fast and lean, then let it be slow, modular, reusable, and intuitive. But hey, if you need or want the efficiency, then power to you. Keras is designed for rapid development and research, not production code. In short, the answer is that it's for the same reason C++ is faster than Python, because the Python interpreter has so much more overhead, as does TensorFlow.
If you want to say more,